Okay, so what is electric current? Um, so as it says here, an electric current involves the movement of electric charge. So if you have charge moving through space, you have an electric current. One important kind of electric current is the movement of conduction electrons that move through conductors. So that would be like the electrons moving through electrical wire. That's one important kind of electric current. Um, let's be a little bit more quantitative about it. So imagine that you have a collection of charges. For convenience, we'll make them positive charges, as shown in the figure here. And the charges are moving to the right. And we imagine that these charges cross through some imaginary surface of area A. So I make this a two-dimensional disk here. And what we're going to do is just count the amount of charge that crosses through that imaginary surface over a certain amount of time. So let's say that we have some amount of charge, I'll call it delta Q, that passes through this surface over some time. I'll call it delta T. The current, so the symbol for the current is the uppercase letter I, and I is defined as simply the charge divided by the time. Okay, well that's not completely true. That's true if we have a so-called steady current. And a steady current just means that it doesn't matter when you do this measurement, counting the charge per unit time, it will always be the same. Okay, so you do it now, or you do it 10 seconds from now, or an hour from now, and if you wait 1 second and count the charge that crosses through that surface, it'll still be the same amount of charge over that time interval. So that's a so-called steady current. So just think of a steady current as being one where there's a steady flow of charge, same amount of charge, passing through the surface every second. So more generally, we can have what we call a time-varying current, where maybe there's an increase in the rate with which the charge moves through this cross-sectional area, or maybe it decreases with time. Okay, so what we do instead is instead of defining the current as delta Q over delta T, we make it a derivative. And this amount of charge, which dQ now is an infinitesimal amount of charge that crosses this surface in this infinitesimal time interval delta T. And that may actually change with time. Okay, so equation 2 is always correct. And equation 1 is just a special case of equation 2. Okay, so now we know what a current means in a more quantitative sense. So we have a new quantity, so we have to introduce the unit, and we call this unit the ampere. Obviously it has units of charge per unit time, so the standard unit is 1 ampere is 1 coulomb per second, okay, as indicated here. Now, one of the strange things about electric current is we define a direction of the electric current. Okay, that's not so strange, but we define the direction as the direction which would correspond to the direction in which positive charge would flow. Okay, so going back up here, with reference to this picture here, whoops, there's the picture, well, there's part of the picture. If we do have positive charge moving to the right, we say the current is moving to the right. If we had negative charge moving to the right, then the convention is the current actually flows to the left. And I know that's kind of a strange thing to deal with, but that is the convention for the direction for a current. Okay? If negative charge was flowing to the right, then we say the current is actually moving to the left. Okay, so let's remember that. Okay, so that's what I say here. The current is for electrons, negatively charged particles, is in the direction opposite to the direction in which the electrons actually move. Okay, so let's look at these pictures down here. What do we have? Okay, if we have positive charges moving to the right, we say there's a current moving to the right. If we have negative charges moving to the left, we also say the current is moving to the right. The current that is a contribution to the current from these negative electrons or negative charges, whatever they happen to be. If you have a block of material here, you have positive charges and negative charges. Maybe the whole material is electrically neutral. The positive charges balance out the negative charges. If you move that block to the right, let's say with a velocity v to the right, the positive charges and negative charges move to the right. Now, if you think about what we've just said about our convention for direction, positive charges contribute to a current which moves to the right. The negative charges, which are physically moving to the right, contribute a current moving to the left, so that the net current will be zero, assuming that you have the same number of positive and negative charges. So that's why when you have an electrically neutral object, same number of positive charges and negative charges, if you move that object to the right or to the left, up or down, yes, you're moving electric charges, but the contributions from the positive and negative charges cancel out, so there's no net current. Okay? That's not going to be the situation, as we will see shortly, when it comes to so-called conduction electrons in metals. But if these negative charges in this picture are not moving relative to the positive charges, then moving that block of material to the right or the left or up or down means there will be no net current. Okay, but obviously we know that there are electric currents that move through materials. So let's talk about, introduce a microscopic model for current. Okay, so what we're going to do is to assume that we have a constant current. Okay, so one where there's a steady current, a steady flow of charge, same number of coulombs per second that cross this cross-sectional area. Okay, so the material that we're looking at here is maybe it's a cylindrical material, and within this cylinder we have positive charges. We imagine there being positive charges that move to the right. Now, this is not actually what's happening with electric currents moving through electrical wire. In that case, we have negatively charged electrons, which flow in the opposite direction. That is, they would be flowing to the left if the current is actually moving to the right. Now, the reason we're considering a case where we have positive charges moving to the right is just that it's a little bit easier conceptually to deal with that, rather than thinking of negative charges moving to the left and having a current moving to the right. Okay, so it's just to make things a little bit easier to deal with conceptually. Okay, so imagine that you have a material in the shape of a cylinder, and we have some number of mobile charges. And how many charges do we have? Well, we have n charges per unit volume. Each one of them has a charge q. Okay, so all these particles we'll assume has the same charge. And let's say that these charges, for some reason, are moving to the right, okay, as indicated in the picture. And they move to the right with a drift speed that we'll call v sub d, and it's the average speed of these so-called charge carriers. Okay, and as I said, each one of these charges has the same charge q, and little n is the number of these per unit volume. Okay, so you might ask, if I have a cylinder of length A, length L, cross section A, how much charge do I have inside the cylinder? Well, it'll be the volume of the cylinder, which is A times L, times N, which is N is the number of charges per unit volume. Okay, so that will simply give you the total number of charges, N times the volume. Multiply that by the amount of charge on each one of those particles. That gives you the total amount of charge inside this cylinder. Okay. Let's say that over some time interval delta t, okay, delta t is a time interval defined so that it's chosen to be L divided by V sub d. And what that means is, for that definition or for that choice of time interval, it means that all of the charges contained within this volume, if you think about it, will pass through this cross-section of the cylinder. They will pass through that cross-section of the cylinder in that time interval. Okay? If you wait for delta t, then the very last charge carrier on the far left side of the cylinder will pass through this cross-section at the end of that time interval. So that means that if you look at this equation here, let me try to highlight it, and combine that with this equation for delta t, if I were to substitute in this expression for delta t into this equation for q, solving first for L, combining those two equations, it would tell me that the amount of charge, now I'm putting a delta in front of the Q, but it means the same thing as this Q up here. The amount of charge that passes through this cross-section is NQ times A times V sub D times delta T. Okay, so it's a lot of quantities there. If I divide delta Q by delta T, hey, that's the definition of the current. Then I have an expression for the current, which is equal to little n, the number of charge carriers per unit volume, times Q, the charge of each charge carrier, times A, the cross-sectional area, multiplied finally by V sub D, the drift speed, the speed with which these charge carriers are moving. Okay, so what does all this mean? A simple illustration. Let's consider, in this problem here, a 5 ampere current flowing through a copper wire of cross-sectional area 1 square millimeter. Okay, so if it's copper, you can look this up in a table somewhere. You'll find that the conduction electron density of copper is this value. There will be 1.1 times 10 to the 29 conduction electrons per cubic meter. Okay, so that's a lot of conduction electrons. There are many more electrons than that, by the way, but those electrons are bound to the atoms. So it's only the conduction electrons, the electrons which are not stuck to the individual copper atoms, that matters here. Okay, so this number here is simply this quantity N, okay, the number per unit volume. So if you want to know what can we do with this information, we could calculate the drift speed. Okay, so if I take equation 3 and I rearrange it so that I have the drift speed on the left, everything else on the right, then I know the current, I know little n, that's this number here. I know the cross-sectional area, 1 square millimeter, and Q is the charge of an electron. You can look that up, that's a known number. Convert all those quantities, if they aren't already, to standard SI units, and you'll get this, this speed here. I guess after I do the calculation, I convert meters to millimeters. So it turns out the drift speed is 0.28 millimeters per second. Okay, so this is a really simple calculation, kind of trivial, but it gives you some sense for what this drift speed would actually be in a real material like copper. Okay, so now that we've defined